Hello everybody. In this video we'll be covering one of the sections in Chapter 2 of our textbook Introductory Chemistry by Tro. This chapter is titled Measurement and Problem Solving. So in this video we're going to go over the basic units of measure. This is where we're going to talk a little bit more about units and their meaning. So units. Units tell the standard quantity to which we are comparing our measured property. Okay? Without an associated unit, a measurement is without meaning. So if you just have a number, it really doesn't mean anything, right? I could say 2, that could be inches, or that could be miles, and they're very, very different things. So if I don't specify what I'm talking about, it really doesn't have a lot of meaning. Scientists use a set of standard units for comparing all our measurements. So there's many different units out there. There's different unit systems. It's really best that we kind of confine ourselves to using a certain set of units. That way we don't spend all our time trying to figure out what the other people's trying to talk about. We can easily compare our results. Each of the units is defined as precisely as possible. So we want to have a really good standard for what each one of the units is. That way we know that we're all talking about the same thing. The standard units. So scientists generally report results in the agreed upon international system. Okay. So a lot of times this is abbreviated SI, and this stands for Système International, which would be like French for international system. And some of the basic units in this would be like, for instance, if we're talking about length, we're going to use a meter. We're going to symbolize that with a lowercase m. There's a capital M we'll be talking about later, so please don't get those confused. We have our mass. That's going to be the base unit for that is going to be a kilogram. That's symbolized kg. Time is in seconds with a lowercase s. And the temperature scale we're going to use is Kelvin, which is a little different than both the Celsius and the Fahrenheit. And we'll talk about what that means, and that's with a capital K. So let's jump in here and talk a little bit about what some of these these different quantities really mean. We'll start with length. This is the measure of a two-dimensional distance between distance an object covers. So this is the distance between 2 points, essentially. The SI unit, as we talked about, is going to be the meter. This is about 3.5 inches longer than a yard, if you're used to that. So a little over 3 feet. 1 meter is equal to 1/10,000,000th of the distance from the North Pole to the equator. The distance between marks on a standard metal rod in a Paris vault, and the distance covered by a certain number of wavelengths of a special color of light. Okay, so we kind of started off with this idea. This is kind of a really historical thing. So really we started off by saying, oh, well, it's such a distance between the North Pole and the equator, but then we realized, well, the Earth isn't exactly a sphere, and it's actually kind of changing a little bit its shape, so that's not going to work. Then we just went to making a metal rod that was the distance of a meter. And then we found out that that metal rod was actually changing in size and shape over time. So we couldn't really use that. Then we came to this value that is really immutable. So if we can limit the certain wavelength, so a certain frequency of light, we can talk about how long that wavelength is. And that is a value of a meter that we really can't change. So that's how we've kind of continued to refine talking about what a meter is. A meter's kind of long, so we commonly will use centimeters a lot of the time, where, for instance, we would be using inches in our system. 1 centimeter is approximately the width of your pinky nail. 1 meter is 100 centimeters. Therefore, 1 centimeter is 1/100th of a meter. There are 10 millimeters in a centimeter. So if you're going to make a really precise measurement, millimeters works really well. I do some woodworking and stuff. I often work in millimeters because it turns out to be about the amount of precision you need to get a good fit. And if we're converting between our standard inches that we've been working with, 1 inch is about 2.54 centimeters. And even that's not even about, they're exactly equal to each other. Here is a setup of a spectrometer that you would use to actually measure the wavelength of light. So this is the kind of setup that we have now that allows us to get this really precise definition for a meter. And here's a comparison of a yardstick to a meter stick. You can see that meter stick's just a little longer than the yardstick. So mass. This is a measure of the amount of matter present in an object. Okay, so there's a little bit of a difference between mass and weight. Weight has to do with the amount of gravity that's being the force of gravity that's being exerted onto an object. So weight changes depending upon your altitude, actually, where your mass is always going to remain the same. But a lot of times they're pretty interchangeable with one another. We'll talk about massing something, and we're basically talking about weighing it on a scale similar to this one down here. The SI unit is the kilogram. It's about 2 pounds, 3 ounces, or so 2.2 pounds. And it's a common, one of the common measurements that we have because the kilogram's kind of big. 2 pounds is pretty big. And we're going to talk about in grams. This is going to give you a usually pretty precise value. All right. If you need to be even more precise, you're going to go down to something like milligrams. So 1 kilogram is 2.2-ish pounds. 1 pound is equal to 453 grams. 1 kilogram is 1,000 grams, or 10 to the 3 grams. 1 gram is 1,000 milligrams, or 10 to the 3 grams. And we have the other conversions here, where 1 gram is going to be 1/1000th of a kilogram, or 10 to the negative 3 kilograms, and 1 milligram is going to be 1/10,000th of a gram, 10 to the 3 grams. So you can see that actually converting within the SI system is pretty convenient, right? You really just wind up having to move this decimal place a certain amount of times, where you get these kind of odd conversions between the SI system and our imperial system that we use often in America. This is the standard for exactly what a kilogram is. We're still working out a better standard, like something kind of based on something immutable like we have for the wavelength of light. But this is just a little platinum piece that is in a vacuum chamber that's kept in Paris. They have noticed that it is losing a little bit of mass. And this is still the standard for a lot of different things, like for instance, gold, on the economic scales and stuff like that. So even this losing a little bit of mass actually could be quite a problem for us. So we're still working out a better value for what exactly a kilogram is. So here's a little activity for you guys. Estimate the mass of a quarter in grams. So how much do we think a quarter weighs? This is kind of a good way of kind of getting started here. And I'm going to say that a quarter is 5.5 grams. And a nickel is actually almost perfectly 5 grams. So kind of gives you a sense of what a gram is, because you have a good sense of what the weight of a quarter is. Time. So this is the measure of a duration of an event. This is a very functional definition. You can get really metaphysical about the idea of what exactly is time or something. But a lot of times in science we just use functional definitions. So time is that thing that a clock measures. The SI unit is seconds, abbreviated with a lowercase s. 1 second is defined as a period of time it takes for a specific number of radiation events of a specific transition from cesium-133. So we're actually defining this based on the amount of radiation given off by cesium-133. 33, which is a kind of, again, immutable thing that is just always going to be the same and gives us this nice standard for what a second is. Temperature. So temperature is the measure of the average amount of kinetic energy that a substance has. So this has to do with how fast the molecules are moving around inside of it, which is kind of an interesting idea of thinking about temperature, because we have kind of a much different relationship to temperature as you know, human beings living in a macroscopic world. But this is what it ultimately means. So a higher temperature is going to mean a larger average kinetic energy. It means that the molecules inside the room, the gas that's inside there, the air, is moving faster. Heat flows from the matter that has high thermal energy into matter that has low thermal energy. So it's going to go. Heat is a thermodynamic quantity that flows from hot areas, places with high temperature, higher average kinetic energy, to cold areas, areas that do not have as large of a average kinetic energy. This is going to happen until they reach the same temperature, and this heat is exchanged through molecular collisions between the two materials. So the reason that heat flows is because the molecules that are moving faster over here have more and more collisions with the slower moving molecules, and that speeds them up, and this process happens more and more until heat moves from, say, like a heating vent over to an area that's further away from that heating vent. So let's talk about a few related units in the SI system. All the units in the SI system are related to the standard unit by a power of 10. Okay, the power of 10 is indicated by a prefix. So this is a little few letters that go at the beginning of the base word. The prefixes are always the same regardless of the standard unit. Okay. It is usually best to measure a property in a unit close to the size of the property. So this is going to reduce the number of confusing zeros. So if you use a really big unit to describe something really small, you're going to wind up with a really small number. And that's usually not desirable. You want to find a unit that is close to the value that you're trying to measure. Okay, so let's talk a little bit about some of the common prefixes that we have in the SI system. We have mega. This is going to be symbolized with a capital M. And this is 1 million of the base unit. Okay, so the base times 10 to the 6. We have kilo, that with the lowercase k, that's 1,000. Deci is a tenth. Centi is 1/100th. Milli is 1/1000th, micro is 1/1,000,000th, and nano, which is 1/1,000,000,000th, or base times 10 to the -9. Let's step through a few of these to make sure that we're on the same page. So if I write kilo in front of something like grams, that's going to be 1,000 times the base unit, or 10 to the 3. And this one is actually confusing, right? Because you would actually think that gram would be the base unit, but kilogram is the base unit in the SI system. I honestly think it's a little bit of a mistake, and it's a little weird. None of the other ones have a prefix on it. So just be aware that this one's a little weird. It's actually kilogram that's the base unit in this case, or you might think it was a gram. Deci is you'd multiply 0.1 by it, so you're taking 1/10 of it, or 10 to the -1. So 1 deciliter is 1.1 liters, or 10 to the -1 liters, whereas 1 liter would be 10 deciliters. Centi is 1/100th times the base unit, 10 to the -2. 1 centimeter is 0.01 meters, 10 to the -2 meters. That means that there is 100 centimeters in every meter. Milli is going to be 1/1000th. 1 milligram is 1/1000th of a gram. 10 to the -3 grams 1 gram is equal to 1,000 milligrams. Micro is 10 to the negative 6, or 1 millionth times the base unit. So 1 microgram, this is a Greek letter mu, that means micro. You might see that is 10 to the negative 6 meters, or 1 micrometer. And that is 10 to the negative, or 10 to the 6 micrometers is equal to 1 meter. And nano is 10 to the negative 9, or 1 billionth of the base unit. 1 nanoliter is 10 to the negative 9 liters. 10 to the negative 9th nanoliters is equal to 1 liter. So which of the following units would be best for measuring the diameter of a quarter? Okay, so a kilometer is a big unit. That's close. That's a little less than a mile. That's not going to do it. Meter, as we've seen, is close to the distance of a yardstick. Quarters are nowhere near yardsticks. That doesn't make sense. Centimeters. This seems about right? I mean, what is it? A half a inch across of a quarter, right? We know that a centimeter is 2.5 inches, so I think this is a good idea. Micrometer, that's really small, right? That's just a millionth of a meter. So I mean, this is going to be many micrometers across. I mean, if you wanted an accurate number, sure, but I mean, just for kind of estimating, that's a little overkill. Megameters are absolutely huge. Those are going to be bigger than kilometers. I mean, that doesn't make sense. So my bet is it's centimeters. And I think that would be the best choice for kind of estimating the distance across there. So you can see what I was saying when I said that you should pick a unit that's going to be kind of similar in scale to the thing that you're going to measure. So volume. So far, I showed you the base units in the SI system and the quantities that they measure. But the first thing you might wonder about after that is there seems to be a whole bunch of other stuff that we need to measure that we don't have units for yet. And what winds up happening is that we can use the base unit that we've had before to derive units. So we can do mathematical manipulation on those base units to get to the other units like volume that we need. Okay. For instance, to do volume, we can take the length and we can cube it. Okay, so we can take, for instance, if I wanted to know the volume of a box, I would take the width, the height, and the length. Okay, 3 units here. I would multiply those together. That would give me the volume. So I'm taking 3 lengths in this case, multiplying them together, and getting it. So this is cubing, or multiplying together 3 different lengths. This is the measure of the amount of space that is occupied inside of an object, the amount of space that something occupies. The standard SI unit is the cubic meter. So you can see it is the base unit of meter cubed. Commonly measured solid volume in a cubic centimeters. Okay, so often we are using actually cubic centimeters as a more reasonable value, because if you think about a cubic meter, that's pretty big, right? That would be a whole, more than a yardstick high, more than a yardstick wide, more than a yardstick this way. I mean, that might be good for like measuring the inside volume of a house, but not a lot of objects, right? Not anything smaller than that. So 1 cubic meter is 10 to the 6th cubic centimeters. That means that 1 cubic centimeter is 10 to the negative 6 cubic meters, or 0.000001 cubic meters. So you see that it's pretty small. It's a small little chunk. If we imagine taking this out, this is a cubic centimeter out of a cubic meter. It's a tiny chunk of it. Another important thing to understand is that a cubic centimeter is the exact same unit as a milliliter. Okay, so 1 milliliter is equal to 1 cubic centimeter. You may also see a cubic centimeter written as like a cc. Like a lot of times they use that in like medicine and stuff. Like you may watch a movie or something like, give me 10 cc's of this medication. They're talking about cubic centimeters or milliliters. All right. If you wanted to measure the volume of a liquid, we have many different tools for doing that in chemistry. We do that a lot. This one here is called a graduated cylinder. You put your liquid into it, and then it has lines as you go up, and you read off the bottom of this guy right here. You can see the top of it's kind of curved. It's called the meniscus. You're going to read off the bottom of that, and where that sits is going to tell you how much volume you have in your cylinder. So one of the things that's going to be really useful to us as we're working through our problems is to have different statements of fact between the relationships between different kinds of units, because we're going to see that these are going to be the basis of our conversion factors. Okay, so if I'm given a value in kilometers and I want to know how many miles it is, I need to know that 1 kilometer is equal to 0.62014 miles. Okay, so I'm not going to go through all of these, but I am going to provide them here for you so that you can take a look at them and refer back to them as we're doing problems and stuff. These are various different conversions that it's going to be useful for you to know, or at least be able to refer back to later. So let's play a little game of which is larger, a yard or a meter, a mile or a kilometer, a centimeter or an inch, a kilogram or a pound, a milligram or a microgram, a quart or a liter or a gallon or 1,000 cubic centimeters. You guys can choose which one you want. So if we take a look at this, we'll see that a meter is larger than a yard. We saw that with our picture earlier. A mile is larger than a kilometer. An inch is bigger than a centimeter. It's about 2.5 centimeters specifically. Kilogram is bigger than a pound. Kilogram is about 2.2 pounds. A milligram is larger than a microgram. A liter is larger than a quart. A gallon is larger than a liter. And a gallon is also larger than 1,000 cubic centimeters. 1,000 cubic centimeters is the same as a liter, so if it's bigger than a liter, it's going to have to be bigger than a gallon, or bigger than 1,000 cubic centimeters. So let's recap here. We're going to always write every number with its associated unit. You're always going to include units in your calculations. You can do the same kind of operations in units as you can with numbers. Okay, so a centimeter times a centimeter is a cubic centimeter. A centimeter plus a centimeter is a centimeter. A centimeter divided by a centimeter is equal to 1. All right, so we'll see how that works out. Using units as a guide to problem solving is called dimensional analysis. Okay, so we need to make sure that after we do our mathematical operations with our units, we wind up with the unit that we should for our answer. And it's very helpful to help us to kind of set up our math, to keep that in mind. Solution map. So a solution map is a visual outline that shows the strategic route required to solve a problem. For unit conversion, the solution map focuses on units and how to convert one to the other. For problems that require equations, the solution map focuses on solving the equation to find an unknown value. The systematic approach. We're going to write down the given amount and unit. Okay, so we're going to write down what we know. We're going to write down what you want to find and the unit. Okay, so we're going to think about what it is we need to figure out. We're going to write down the needed conversion factors or equations. So we're going to go back to those tables I gave you earlier, and we're going to find those facts, those equations that allow us to interconvert between the two different units. We'll write down these equivalent statements for each relationship, and we'll change the equivalent statements to conversion factors with starting unit on the bottom. All right, so we'll see how that works out in just a second here. we're going to design a solution map for the problem. So we're going to order the conversions to cancel the previous units, or arrange the equations so that we can find the amount that we need. So it's isolated. We're going to get the thing that we want on one side of the equation all by itself. We'll apply the steps in the solution map. We'll check that the units cancel properly, and we'll multiply terms across the top and divide by each bottom term. We'll determine the correct number of significant figures so that we know how to round our answer in the end. And then finally, we'll check to see that the answer is reasonable. All right, that it has the correct size at some reasonable value, and that it has the right unit that we expected for our answer. All right, so let's think about one of these. So if we have an Italian recipe for making creamy pasta sauce, calls for 0.75 liters of cream, and that would be reasonable that it's going to do that because we're talking about an Italian recipe. Italy is in Europe. They use the metric system there, so they're going to have something metric in their recipes. Your measuring cup measures only in cups because we're in America and we use cups. How many cups should you use? All right, so what are we given? We were given that we have 0.75 liters, and we want to find the right number of cups, right? So we're going to need to collect our needed conversion factors. We know that 4 cups is equal to 1 quart, all right? There are 8 ounces in a cup, 4 cups to a quart, 4 quarts to a gallon. We know that 1.057 quarts is equal to 1 liter. All right, so now we have a pathway between cups and liters through quarts. And now we can write a equation that's going to allow us to get to the cups. So this is what we were talking about where we say we're going to convert these statements into conversion factors. Okay, so what I've done is I've rewritten this statement that 1.057 quarts is equal to 1 liter as a fraction here, okay, where I have quarts in the numerator and liters in the denominator, okay. Now when I take liters and I divide them by liters, right, because this number is essentially in the numerator here, every number is itself over 1, right, I'm going to cancel these liters, and I'm now in quarts, okay? But I don't want quarts in my final answer. I want cups, so I need to do the next step here, the next conversion, where I say 4 cups is equal to 1 quart, and I make that into a fraction here, where I have cups in the numerator and quarts in the denominator. I can now cancel my quarts, and I'm now in cups. Mathematically, I'm going to take 0.75. I'm going to multiply by 1.057. I can divide by 1, but that won't change the number, right? I'm going to multiply by 4, and then I'm going to divide by 1. Again, won't change the number. When I'm done, I will have 3.17. And the unit will be cups, because as we can see here, we've canceled those other units. And so you're always going to order these, right? I could have written liters in the numerator and quarts in the bottom, but I chose to do it this way so that I will cancel those units, all right? Now we can do a little check here. 3 cups. So given that a liter is very close to a quart, and we know that there's 4 cups in a quart, 3 cups and some change is a reasonable number here, okay? And we can use our measuring cup to measure out about 3 1/5 cups, okay? So let's do a little practice here. I want you guys to pause the video and write a conversion between 30.0 grams and ounces, using the fact that 1 ounce is equal to 28.32 grams. So our solution here, we're going to start with the known quantity that we got, our 30.0 grams. We're going to rewrite our statement in the form of a conversion factor. We're going to put grams in the denominator so that we cancel those. We're going to put ounces in the numerator. We'll cancel our grams. Okay, we'll have ounces left over for the answer. Mathematically, we're going to do 30 divided by 28.32 multiplied by 1. We'll come up with 1.06. Since we're taking 30 and dividing it by a number a little less than 30, it seems reasonable we'll come up with a number that is a little bit bigger than 1. Let's take a look at this one. We have a circle that has an area of 2,659 square centimeters. What is the area in square meters? All right, so I showed you before the conversion factor between centimeters and meters, but I do want you guys to recognize a little trick that we can play. So let's say that we don't remember the conversion from before. All we remember is that 1 centimeter is equal to 0.01 meters. We can take that fact and we can take both sides of this equation and square it. Okay, so here we're squaring the 1 and we're squaring the centimeter unit. Here we're going to square the 0.01 and we're going to square the meter unit. Once we're done with that operation, we can get a relationship between square centimeters and square meters, where we see that 1 square centimeter is equal to 0.0001 square meters. Okay. Now we can use that conversion in order to convert between the known value of square centimeters to the value of square meters. Okay, so we'll cancel our square centimeters. We'll perform this operation that is essentially multiplying by 0.00001, which is going to mean that we're going to move this decimal place over 4 places, and we get that this is equal to 0.2659 square meters. So this is a way of taking a conversion factor that we know and sort of deriving a relationship from it.